Hello everyone and welcome to lecture today. So today we're going to be talking about a little bit more number theory. Specifically, we're going to be going over some ideas and properties of prime numbers and coprime numbers, which we defined before. And these results that we're going to get today are going to be very, very useful in general, but also specifically they'll be useful in our applications to cryptography, as well as in many other applications. And I guess one of the big things that we're going to be doing by the end of the lecture is learning how to solve basic congruences, so congruence equations. Specifically, these are equations of the form AX is congruent to B mod M. Right? And this is looks similar to an equality here, but this is saying that AX is congruent to B mod M. But it turns out that under certain circumstances, specifically when the A and M are coprime, right? Or we'll see today the greatest common divisor of A and M is 1. When this is true, we can actually solve this equation for X. Now, I want to note here that when you solve this, right, if you solve this for X, you can't just divide by A because of the previous work on congruences. Right? You can only go forward with multiplication. With congruences, you can't go backwards. You can't divide unless you have something very special, which is the coprime, or the thing that you're dividing is relatively prime to the modulus M. So we shall see this as we move along in the lecture. So at the end of lecture 14 part 2, we ended up going through and developing two definitions. The definition of a prime number, which is a number whose only positive factors are p, so the number itself, and 1. And a composite integer, which is an integer that is not prime. So an integer that has factors that are different than itself and 1. We also introduced the definition of coprime, or relatively prime, which means that the only positive integer that is a divisor of both of these two integers, a and b, is 1. These are going to be super important concepts today, and also, when we kind of move along into applications such as cryptography. But let's go through and write down the first big theorem here, which is the fundamental theorem of arithmetic. And this is stated as follows. We have that every integer such that n is greater than 1 can be written uniquely as a prime, this is case 1, or the product of two or more primes. Where the prime factors are written in non-decreasing order. Right, so we can see this very, very clearly that, say, take 15, we can express as 3 times 5. 30 we can express as 2 times 3 times 5, and so on and so forth. Right? So the idea here is that we want to prove this. It's very useful, and everyone kind of intuitively, I think, understands this idea. I'm not sure if anyone's ever seen a formal proof of this, but we'll start off by stating that we have to prove two things here. Specifically, this is going to be that you need to prove the existence of this factorization, and then we also have to prove uniqueness. So we're going to split this into two parts, and right now we can go through and prove part 1, or existence, of this factorization relatively easily using a proof by induction. And specifically, this is going to be strong induction. And this is one of those cases where it's actually you see that using strong induction is actually going to be a lot easier and in some sense necessary here to avoid certain pitfalls in the proof. So this is the reason that we talked about it in the induction lecture. So we start with our base case, or base cases. And this is just going to be, we have that 2 is equal to 1 times 2, 3 is equal to 1 times 3, 4 is equal to 2 times 2. And I think this is enough base cases to get, give you the idea, because we have that for 2 and 3, they're both prime, so they can be written as 1 times itself. And then 4 is a composite number, and it can be written as 2 times 2, which is just the 2 lower primes. So it's a product of 2 or more primes. So the inductive hypothesis here this is strong induction, is going to be that there exists an n such that for all n less than or equal to, or for all k less than or equal to n, k can be factored as above. So either 1 or 2. And what we have to do is we have to show that this implies that n plus 1 can be factored as above. So either 1 or 2 holds for the integer n plus 1. So to do this, we assume, we're assuming the inductive hypothesis. We basically have two cases that we got to look at. The first case here is that n plus 1 is prime. Call it P, in which case n plus 1 is equal to P, or 1 times P, and this is satisfied. The theorem is done. N plus 1 is factorable as a prime times 1. So the interesting case here is case number 2, because this is the case where we actually have to use the inductive hypothesis. This is n plus 1 is a composite, if this is the case, then there exist integers a and b such that a is strictly less than m and b is strictly less than m, or n plus 1 and m plus 1. These are in positive integers, and n plus 1 is equal to a times b. But by the inductive hypothesis, a is equal to p1 times p m, and b is equal to q1 all the way up to ql for primes p and q, because a is less than or equal to m and b is less than or equal to m or n. And by the inductive hypothesis, that means that we can factor them like before, or as up here in the assumption of the theorem. So because of this, this is going to be q1 all the way to ql for b times p1 pm, and we might have to reorder these p1s and q1s to reorder this, but because of the commutativity of addition in the integers, this represents a factorization of m plus 1, which is the required prime factorization for the theorem. So this is a very, very nice inductive proof using strong induction of the fundamental theorem of arithmetic. And it's not that complicated. It's not that hard to understand as long as you understand induction. So the idea here then is that for part 2, right, this is going to take a little bit more. So we will prove this later. Specifically, what we need to develop is this idea of what's called a Bézout coefficient to calculate the GCD, the greatest common divisor of two values. So we'll get into this a little bit later. Now, there's a pretty useful theorem in the book that's neat, and this is proved by contradiction. I'm not going to go through and do the proof, but it'd be a good exercise to go through and take a look at for yourself. This is if n is a composite integer and, or sorry, not and, then n has a prime divisor less than or equal to the square root of n. It just kind of gives us a relationship between the a composite integer n and its prime divisors. So the proof of this is in the book. Right, this is in chapter 4.3. However, this is a useful theorem for a lot of different reasons. For instance, if you take the contrapositive of this statement, it's going to be that if n does not have a prime divisor, less than or equal to square root of n, then n is not a composite integer, or n is prime. This is an if-then statement, the contrapositive of an if-then statement. If it's if P then Q, this is if not Q then not P. So we can use this to show that 101 is a prime. Specifically, we look at the square root of 101, right? And the only primes not exceeding, so less than or equal to the square root of 101 is going to be 2, 3, 5, and 7. 101 is not divisible by any of these. Right? So therefore, it follows that 101 is prime. This is a pretty cool example. One useful tool for finding the prime numbers computationally is called the sieve of erasthenes. And the idea here is relatively simple. So you start by making a grid, just kind of a long listing of numbers. It could be in a grid format from 1 to 10, 1 to 20, or 11 to 20, 21 to 30, and so on and so forth. But the idea here is that you make this grid and then you underline all the values that are divisible by subsequent primes. So this is called the sieve of erasthenes, and this is really just the first step of the sieve. Sieve of erasthenes. Step 1. You underline integers divisible by 2 other than 2. That's 4, 6, 8, 10, 12, 14, 16, 18, and so on and so forth. And then you do the same thing for integers divisible by 3. That's going to be 3, 6, 9, 12, 18, and so on and so forth. And then you do the same thing for five, I get 5, 10, 20, 15, so on and so forth. And so the idea here is really cool. What you're getting when you're doing this process is what's called a sieve, or it's kind of like you're kind of filtering out all of the prime numbers up to a certain value. So in this case, 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. These are the prime numbers. And you see that there's no regular distribution of primes, and this is a big question in mathematics: is what is the distribution of the primes, or is there a way to predict the primes? And the idea is that this is still an open question. There are many huge open questions still to this day in mathematics about the prime numbers. Very, very, very big, deep questions in number theory. This is a very neat thing to see, and as far as the application of prime numbers, right? The big application here is to cryptography. And this is one of the reasons cryptography works. I should say RSA cryptography. It works because there's no nice method of factoring large prime numbers. It takes a very, very long time to do. So the idea here is that this is why RSA cryptography is based on this process. And very closely related to modular arithmetic. So we have a big theorem. You could ask, is this going to continue? Are there infinitely many primes? And sure enough, there are infinitely many prime numbers. We can do this relatively quickly using a proof by contradiction. We assume there are finitely many primes, and we can list these out, P1 up to Pn, and we'll let Q be the number of P1 times P2 times P3 times Pn plus 1. So this is just the multiplication of all of our finitely many prime numbers with the 1 added to it. We have that by the fundamental theorem of arithmetic. Q is prime or it can be written as a product of primes in non-decreasing order. However, in the case of 2, none of the primes divide Q, because Q is the product of all the primes, which this product is divisible by every single one of the primes, but 1 is not divisible by any of these primes. So none of the primes pi, where I is between 1 and n, can divide Q. This is by construction, because Q is equal to product of all of the prime numbers plus 1. Therefore, there is a new prime P star that must divide Q, so be a prime factor of Q, or be Q itself. This is a contradiction because the listing P1 through Pn was supposed to be all the primes. Right, so therefore we conclude that there are infinitely many primes. Note that in the proof we do not state that Q is prime. Furthermore, in the proof is a non-constructive existence proof, that given any n primes, there's a prime not in the list. For the proof to be constructive, you would have had to explicitly give a prime not in the original list of n primes. And a lot of mathematicians have an issue, and specifically logicians have an issue with non-constructive proofs. But I think this is the quickest way to go through and show this. Proof by contradiction is a very valid tool, but you should realize that it's not constructive in the sense that you're not explicitly showing the existence of something. You're just kind of using a logical contradiction to show that there must exist something. So moving on, this idea brings up a number of different new ideas, and we've proven that there's just infinitely many primes. We can ask how many primes are less than a positive number x, or what is the distribution of primes? And this question has interested many mathematicians over the years, but it's still an interesting question today. That is, in some sense, we have a certain idea, but there's still a lot of open questions. One of the things that we can do is define a function called the prime counting function. This is a function from the positive prime numbers into the positive prime numbers, such that pi of x is the number of primes less than or equal to x. And there's actually an interesting theorem that was conjectured but not solved by Gauss and Legendre. Wasn't proved until a little bit later, called the prime number theorem. And this is that the ratio of pi of x and the function x over natural log of x approaches 1. As x grows without bound. And we're not going to prove this here, but it's important, a very important theorem to write down. I want to note that this is actually another type of asymptotically equivalent in some sense. It's stronger than just pi of x grows on the order of x over ln of x. This is actually has a different notation for it, and it's what's called asymptotically equal to. So what this theorem is saying is that the prime counting function pi of x is asymptotically equal to the function x over natural log of x. The notation that is reserved for this in many texts and sources is just tilde. So pi of x tilde x over ln of x. And if you know what a limit is, this actually is equivalent to saying that the limit as x goes to infinity of pi of x over ln of x over ln of x is equal to 1. This is just stronger, much stronger condition than just saying that pi of x has the same order of growth as x over ln of x. And what's interesting is that if you know what a limit is, all of the previous things that we've done in regards to order can be rephrased in terms of limits. But because this involves calculus, I haven't gone over this, and really, in some sense, it's better in a discrete mathematics course to go over the fundamental definitions, because you really get a taste for what the statement is saying and how to prove it. But I will kind of give you a picture here to sort of visually verify this so that you can see this result right here. So this is a plot of the prime counting function pi of n for a large number of values up to 60. And you see that at 1 it's 0, at 2 it's 1, at 3 it's 3, at 4 it's 3, and so on and so forth, compared with a plot of function x over ln of x for x larger than 2 right here. And you can see very clearly that these two things have very similar growth. And the growth only gets more and more close to one another as you get larger and larger. You have to get really large in order for these to match up really well. But this is a very interesting example. There are a lot of open problems about primes, some of which I'll just kind of briefly mention here. These are unsolved problems to this day about prime numbers. Goldbach's conjecture is conjecture by Christian Goldbach in 1742, which he posed in a letter to Leonard Euler. And he conjectured that every odd integer is the sum of 3 primes. I should say every odd integer greater than 5. And in Euler's response, he replied that this conjecture is actually equivalent to the conjecture that every integer for n greater than 2, strictly greater than 2, is the sum of 2 primes. And this is called Goldbach's conjecture, that every integer n strictly greater than 2 is the sum of 2 primes. And this can be checked in a relatively straightforward manner for small numbers, small even numbers. And although no proof of Goldbach's conjecture has been found, most mathematicians believe it is true. The twin prime conjecture is a conjecture on what are called twin primes. twin primes are pairs of primes that differ by 2, and the twin prime conjecture asserts that there are infinitely many twin primes. And this has been verified for a large number of twin primes, but it actually leads to a slightly weaker theory or theorem known as the bounded gap conjecture, which asserts that there's an integer n for which there'll be infinitely many primes that are at a length of n gap away from each other. And I remember back in 2013, the entire world was super surprised by the work of Yitang Zhang, who was a 50-year-old adjunct professor at the University of New Hampshire, who hadn't published a paper since 2001, and he released a paper that proved the bounded gap conjecture in 2013. It was amazing. In particular, he showed that there is an integer n less than 70 million, such that the bounded gap conjecture is true. And his work was expanded upon by a team of mathematicians, including Terence Tao, who effectively lowered Zhang's bound by showing there is actually an integer that satisfies the bounded gap conjecture that's less than or equal to 2046. Furthermore, they were able to show that if a certain, another conjecture was true, it could be shown that n, this gap, is less than or equal to 6. And this is the best possible estimate that could be proved using the methods introduced by Zhang. It uses some very advanced ideas, but it was absolutely incredible. Immediately after his breakthrough in 2014, UNH appointed him to a full professorship, and he stayed at Princeton for a semester in 2014, and then he joined the University of California, Santa Barbara in fall of 2015. But it's a pretty incredible story. The last open problem that I want to talk about is fairly complicated, but it should be mentioned because it's very important, and it's not necessarily a direct statement about the prime numbers, but it has a super close relation to them and is actually extremely related to the prime numbers. This is called the Riemann Hypothesis. And this is actually one of 10 problems called the Millennium Prize problems, for which there's a $1 million prize for proof or disproof of the conjecture. And so the Riemann hypothesis is based around what's called the Riemann zeta function. Which is a function of zeta of s, function of a complex variable. S is a complex number here. And when the complex modulus of s is greater than 1, it's the sum from 1 to infinity of 1 over n to the s. So it's the sum of all positive integers raised to the power of a negative complex value. So this function can actually be what's called analytically continued to all complex values. So the value of the function can be extended to all possible complex inputs of s except for certain poles. And the idea is that this hypothesis is centered around what are called the non-trivial zeros of this function. So this function has a number of different points where it has a zero value, And for a visualization of the function, you can see that right here. So this is for all complex inputs. The color here represents, in some sense, the value of the function. And there are zeros, called the trivial zeros, along this line right here. But the non-trivial zeros are any the zeros that don't lie on this line right here, or the imaginary value being 0. And sure enough, we can actually prove that all of the non-trivial zeros must be between a real part of 0 and a real part of 1. But the conjecture, or the hypothesis, is that all of the zeros lie on the line where the real part of the complex input is 1/2. So I'm going to do my best to put this at 1/2 right here. The Riemann zeta hypothesis is the hypothesis that all of the non-trivial zeros lie on this line. A more zoomed in picture of this critical strip, it's called, is right here. And this actually has a lot, many very important implications in number theory, specifically because of what's called Eulers' product formula, which was shown in 1737 by Leonhard Euler. He proved the identity that zeta of S is actually equal to the product, where P is prime, of 1 over 1 minus P to the negative S. So it's an infinite product of all the primes of 1 over 1 minus P to the negative S. And there are many results that actually, if this hypothesis is true, are also true as a result of this hypothesis. And this would also render crypto systems based on RSA cryptography not as effective, because in some sense this would allow us to factor very large integers n. But this is a very important thing to at least know about. So what I want to do now is cover a very useful tool, introduce a very useful tool called the greatest common divisor of two integers a and b. And this is directly related to the idea of coprime introduced before. So for integers a and b, not both 0, the largest integer d such that d divides a and d divides b is called the greatest common divisor of a and b. And for notation, you denote this as GCD of a comma b. And for an example, the GCD of 24 and 36 is going to be equal to 12, because if you factor 24 and 36 into primes, right, the common divisors of 24 and 36 are 1, 2, 3, 4, 6, and 12. right? Those are the positive common divisors of 24 and 36. Therefore, the GCD of 24 and 36 will be 12. And it's relatively straightforward to go through and show using our definition of coprime or relatively prime that integers a and b, this is actually the definition of relatively prime in the book, which is a little bit different than our definition of relatively prime, but it's relatively easy to go through and show that integers a and b in Z are coprime if and only if the GCD of the two integers is 1. And it turns out that this notion is super important for solving congruences, which is something we're going to talk at length about, for crypto systems, so RSA crypto systems, and all sorts of other things. But one of the tools that we have for measuring, in some sense, the coprimeness of integers is what's called the Eulers Torsion function. Or the Eulers phi function, done by capital Phi. This is useful in RSA crypto systems. It's useful in abstract algebra, but it's basically a function from the positive integers into the positive integers, similar to our prime counting function pi, such that phi of n for some positive integer is defined to be the number of positive integers less than or equal to n that are relatively prime to n, or the GCD of those integers in n is equal to 1. We can get a direct plot of this function relatively easily. And it's useful to point out here that the prime numbers are exactly the numbers that lie on this line right here, line y equals x minus 1. So this is Euler's Torsion function from 0 to 100. We expand our plot. We can see a plot of it from 0 to 1000. But this is a very useful function that satisfies a number of very interesting properties and useful properties. One of the most useful properties is that it's multiplicative, in that phi of m times n is equal to phi of m times phi of n.